While instructions tell the CPU what to do, directives, also called pseudo instructions, give directions to the assembler. For example, the move LW and the add LW instructions are commands to the CPU, but EQU, ORG, and END are directives to the assembler. The following presents some more widely used directives of the PIC and how they're used. EQU, or equate. This is used to define a constant value or a fixed address. The EQ directive does not set aside storage for a data item, but associates a constant number with a data or an address label so that when the label appears in the program, its constant will be substituted for the label. The following uses EQ for the counter constant, and then the constant is used to load the working register. So we can see here from the instructions, count EQU at 25, and then it goes on and on and on. That's what the dots are for. And then we get down to the command that says move LW count, so that's the name of that line, it matches that line. Move the value then to the working register 25H. When executing that instruction, move LW count is the register, working register, will be loaded with the value of 25 hex. What's the advantage to using the EQ? Assume that a constant, a fixed value, is used throughout the program, and the programmer wants to change its value everywhere. By the use of EQ, the programmer can change it once, and the assembler will change all of its occurrences throughout the program, rather than have to search the entire program trying to find every occurrence. Set is a directive used to define a constant value or a fixed address. In this regard, the set and EQ directives are identical. The only difference is the value assigned by the set directive may be reassigned later. To get more practice using the EQ to assign fixed values, let's take a look at the following example. You can see that we've got in given hex values first, data 1. So we have data 1 EQ 39. The hex data is the default. Data 2 EQ 39, another way for the hex. Data 3 EQ 39 hex, another way for the hex. It's redundant. Data 4 EQ H single quote 39 close. So you can see we're given an example of each of the ways that an EQ can be written in hex. We do the same thing in binary, decimal, and ASCII. So you can look at these and you can tell in each case what the value is for each data value and the EQ that is set for each particular value and each instruction. We use DB to allocate code ROM memory locations for fixed data such as ASCII strings. We'll see more about this later. Using the EQ for SFR address assignment, EQ is also widely used to assign FSR addresses. So we can take a look at in this case. We've got an example here, again, called a line called counter. We're going to equate 0, 0, 0, the counter value to start at 0. At port B, the equate value is given as 0 FF6, the SFR port B address. The move LW counter value then is looking back at that first line and is setting the working register to 0. Move FLWF port B then moves a port B value that has been set at 0, 0 as well. Increment F port B to a file F, we're saying that the port B value has now been incremented by 1. Increment port B F, we've incremented again, stored the value at port B, now it's 2. Increment port B F, we've incremented it one more time at port B, and now the value is 3. So in this case, you can see we use the equate value to set it up, and then we use our instructions just as we've learned them. The above was for the PIC-18 family. If you use a different PIC controller, such as the PIC-16, where the port B is at a different address, you then change the EQ address for port B and reassemble the program to run it. So if we take a look here at the code below, counter EQ set to 0, so that value is set. Port B EQ at 7 then is the address for the PIC-16. Now we move the value, literal value for counter and it's set at 0, so we look back at that first line. Move the working register to file port B. Now the port B has a 0 as well, and then we do the same thing. We increment by 1, it stores that value at port B. We increment it again, it stores a 2 at port B. We increment it again, and it stores the value at port 3. So those are the first two. We'll look at the others here as we go.